Our last speaker today is David. He will talk about the porous media equation we already saw today and about new techniques solving it. And he's in Milan, I think.
Yeah, Polytechnic. So, hi everyone. I'm Davide Losapio. I'm in the third year of PhD at the Department of Mathematics in Polytechnic di Milano. And I belong to the MOX group. And today I'm going to describe an improved embedded method for flow in fracture porous media with numerical upscaling and machine learning. And this is a work done with the help of my supervisor, Scotti. So, the study of flow in fracture porous media has many applications, going from carbon capture and storage, groundwater contamination, or also oil production and migration, just to cite a few, but there are obviously many more. We start by giving some basic definitions about flows in fracture porous media. And firstly, we define fractures. So fractures are discontinuities in a rock system, which are typically caused by stress condition, which could be of the traction or compression type, or of the shear type. And these fractures can be either empty or filled maybe with some other material different, typically from the surrounding matrix. And so they introduce some strong heterogeneities that influence heavily the flow pattern in the porous medium. The main assumption that is typically done is that the fracture aperture is much smaller than the other dimension of the fracture itself, so with respect to, for example, to the extension of the fracture, and it is also very small compared to the matrix dimensions, compared to the scale of the matrix dimensions. Systems are also geometrically complex, as we see in the figure. Typically, these are, let's say, real fracture systems. And typically, what is easy to do is performing simulation with so-called conforming grids, meaning that the elements of the grids are conforming to the fracture surfaces. So the edges of the cells or the faces of the cells will coincide with the fracture surfaces. Obviously, this means a high number of cells in the mesh, and so a high computational cost of the overall procedure. And so what we do now, what I do in my work is focusing on the so-called embedded methods, where instead the fractures can cut the grid, so that we extend, let's say, we transfer the complexity from the grid to the modeling part, so to the equations. And these methods are also generally efficient and robust, and they allow for general permeability fields. So here we consider, say, the first type of embedded method that was introduced was the one introduced by Lee and Lee, which is here, the paper shown here. And we consider here the Darcy type governing equation, which describes a single-phase incompressible flow, and in particular here we describe 2D systems. So these equations are linear elliptic equations in the pressure P, where the capital lambda is the permeability tensor, mu is the dynamic viscosity, and the uppercase QM and QF are two generic source terms in matrix and fracture, and the lowercase QMF and QFM are some coupling terms that, let's say, gives us the idea of the matrix fracture flow exchange. Obviously, this system must be supplemented with appropriate boundary conditions. And in order to discretize this system of equations, we use finite volume methods. Finite volume methods, the fluxes at the interfaces of the cells are computed as the product of a transmissibility times a pressure difference. So in particular in this model, the matrix fracture transmissibility is a function of the fracture surface inside the cell, inside the matrix cell cut by the fracture, a mobility term, which is typically the ratio between permeability and dynamic viscosity, and an average distance term, which means which stands for the distance, the average distance between points in the matrix and points belonging to the fracture surface. This method has some limitation. The main one is that it is applicable only for highly permeable fracture, so one with the lambda has very high values with respect to the lambda of the matrix. And a linear pressure distribution is assumed around fractures in order to get this expression for the matrix fracture transmissibility. What is done next this is an improvement of the previous method. It's called projection-based EDFM. Is a method that is applicable for any conductivity contrast, so also impermeable fractures can be captured accurately. And what is done is that new connections between fractures and the non-neighboring matrix cells, because here maybe we don't understand much, but this is orange color, and say these new connections are taken into account after a projection procedure, where the projection is that of these fracture cells in green that create this projection path highlighted in red, and the constraint is that this projection of the fracture should be continuous, should be done so that the path has no holes. And then the matrix fracture and near fracture matrix transmissibilities are modified with respect to the previous method to correctly represent both barriers and conduits. So these are the expression of the new matrix fracture transmissibilities, and that's the modification of the matrix transmissibility, where we see that we have this new term, so the projected areas that go into this new matrix fracture transmissibility, and they are subtracted from the near fracture matrix transmissibility, so that when a fracture cuts entirely a matrix cell, then this quantity eventually goes to zero. Okay, so what I've done in my PhD studies, one of the works that I've done in my PhD, is that of conceiving a new method. It's called local EDFM, which tries to improve the matrix fracture coupling by relaxing the linear pressure distribution assumption, and it should be also obviously applicable for both permeable and impermeable fractures. So in order to achieve this, local problems, different types of local problems are solved in order to get a new matrix fracture and near fracture matrix transmissibilities. This procedure could be, let's say, very costly, especially if we have grids with a lot of elements, so very fine grids. And in order to reduce the computational burden of the method, we all employ neural networks. This is in the second phase, obviously. So we introduce two types of local problems, so a matrix fracture one and a matrix one. What we assume here is that only one fracture, I consider only one fracture in the local domains, and the fracture should not lie on the domain boundary. So for the MF local problems, let's say I've taken inspiration from the so-called numerical upscaling techniques for fracture systems. Here we have some papers about the subject, where slightly compressible single-phase flow equations are used in order to get the upscaling of the transmissibility. And here in particular we consider impermeable systems, so the boundary has no flow conditions, and we have a constant source term which is strictly positive only inside the fracture, so inside the bed inside the green portion. So in this case, it's like we are continuously injecting fluid into the domain so that the overall pressure in the domain rises, and after a certain point it will be reached a so-called pseudo-steady state condition, which means that the transient term reaches a constant value, so the derivative of the pressure reaches a constant value, and that's so in a typical upscaling procedure, one wants to solve this equation when this pseudo-steady state condition is reached. But it could be shown that that finding the pseudo-steady state solution of this system is equivalent to solving this other problem, which is instead stationary, but it has a modified source term, which depends on the previous source term, fracture porosity, compressibility, and the pseudo-steady state constant. It should be noted that porosities and compressibilities are assumed to be constant in all the process of the derivation of the equation. Obviously, we also have to set a condition in order to get the uniqueness of the pressure, since we have homogeneous Neumann boundary conditions here. And when numerically solving the problem, obviously the second formulation, so the stationary one, is preferred in order to save computational resources. Going now to matrix-matrix local problems, so we instead solve Darcy-type governing equations, so like the original one that we saw before, but with pressure flux conditions on the left and right side of the domain respectively, and on the other portions of the boundary of the domain we impose no flux conditions. So obviously here I have depicted the case of a vertical interface, but in the case of an horizontal interface the definition of the problem is easily adapted. Okay, now passing to the discretization of the local problems. Here we solve these problems with a conforming method through routines that have been implemented in a software that is called MRST, which stands for MATLAB Reservoir Simulation Toolbox. And these methods employ what are called triangular hybrid grids, where hybrid means that they are lower dimensional in the grid geometry, lower dimensional with respect to the matrix elements, so the triangles here, but they are equidimensional, so the same dimension of the matrix grid when doing computation of the transmissibilities. And there's also here the possibility of choosing between a simple two-point flux approximation scheme where the flux is computed using only two values of the pressure, and or let's say a multi-point method which instead has a larger stencil. So in this case, 6 values of the pressure. So this is a typical solution for a permeable fracture, for the matrix fracture, the matrix local problem. Okay, the values of the pressures are fictitious, but this doesn't have any impact on the calculation of the transmissibility, since it is a ratio between flux and average of pressures. Here instead we see the solution when the fracture is impermeable, and let's say the effect is clearly visible on the matrix local problem. So the workflow of the method is as follows. So when we have to solve these local problems, we have to solve them whenever a matrix cell is cut by a fracture, we solve a matrix fracture local problem. While whenever a face of the matrix grid, so the red one, has at least a neighbor cell cut by a fracture, then a matrix local problem is solved. And after solving these local problems, as let's say in a post-processing phase, we compute the transmissibilities in this way. So as the absolute value of the sum of fine-scale fluxes divided by the difference of average pressures in the respective cells. So obviously, when we have fine grades, this procedure could be very costly. And so the idea is that of using neural networks in order to reduce, let's say, the cost of the procedure. And so local problems are being solved in an offline stage by examining different fracture configurations and also changing the permeability contrast between fractures and matrix. And then these results, these samples, are used to train a feed-forward neural network, which is often used for functional regression tasks. And I've used, in this case, the deep learning toolbox of MATLAB to do the job. So, coming at the architecture of the problem, I've decided to use the same architecture for both problems, just to let the things be simple. And in particular, in the input layer, I've considered 5 neurons. So the first 4 neurons represent the coordinates of the vertices of the fracture, while the other neuron represents the logarithm of the permeability ratio. Then, in the hidden layer, I considered only one hidden layer, since say it suffices to let the neural network behave as a universal function approximator. And this number of 40 neurons has been chosen through a trial and error procedure. Then on the output layer, we have the logarithm of the transmissibility. But why I use the logarithm? That's because, and that's for various reasons. It allows us to vary the permeability ratio by orders of magnitude. It also allows us to better cover the range of variability of the transmissibility. And the most important thing, it allows the possibility of obtaining negative transmissibility values when performing the evaluation of the network. So here I describe, let's say, the sampling of the input parameters, in particular the coordinates of the vertices of the fracture should lie in the square 1 by 1 for the matrix fracture local problem, or in the rectangle 2 by 1 in the matrix local problem, while the permeability ratio has been chosen to vary in a range that goes from 10 to the minus 8 to 10 to the 8. And these coordinates have been chosen so that they satisfy some specific constraints. So at least one of the vertices should lie on the domain boundary. The vertices of the fracture shouldn't lie on the same boundary edge, and the number of samples for the cases that I will show now in the next slide should be equal. And moreover, the permeability ratio has been chosen to be evenly spaced in a logarithmic way. So, in the matrix fracture local problem case and in the non-immersed fracture case, so for fractures that cut the domain from part to part, each boundary edge counts as a case, while for the immersed fractures, each boundary edge cell connection counts as a case. Going down for the matrix local problem and non-immersed fracture, each unit boundary edge connection counts as a case, and lastly, for immersed fracture, each unit boundary edge cell connection counts as a case. So for a total of 10 cases for matrix fracture local problems and 25 cases for matrix local problems. And during data generation, some samples have been discarded, so the one that have immersed vertices that fall too near to the boundary, or vertices on the boundary that fall too near to the coordinates of the domain. These are discarded because the local grid refinement in these cases is too heavy, let's say, and I would have a local problem with too much, a local grid with too much elements. So in order to train these neural networks, I've used the Lavender Marquardt algorithm, which is the standard algorithm used when performing functional regression tasks. And the data is randomly divided in this way. So in a training set, we have the 70% of the samples in the validation one, we have the 15% of the samples, and that's the in the test set. We have the 15% of the samples, and as a performance function, we've used the standard mean squared error. And while on the right, we have an example of a training procedure where we see that no overfitting is present, since the curves for all the sets have more or less the same trend. So here we give some results for the case of the matrix fracture local problem, and employing one in the layer with 40 neurons. So we see that the result, the fit is pretty good, the fit between the desired outputs and the target outputs. While for the matrix local problem, we have, let's see, the results are a bit scattered especially around the target one. So in order to improve these results, what I've done is that we're adding a layer with another 40 neurons, and the results are obviously better, but the training time gets higher. So also for matrix local problem, we have a good result, but obviously we have to observe that the training time is a one-time procedure, and the evaluation of the network lasts a few seconds, while solving many local problems is obviously a more expensive procedure from the computational point of view. So now passing to some numerical examples, I consider an horizontal fracture case and an oblique fracture case, and the domain is a 1×1 square, and the boundary conditions are those shown in the figures. So I considered 4 cases, 2 permeable fracture cases and 2 impermeable fracture cases. The fracture aperture is set to 10⁻⁴, and I compared the performances of the 3 methods. So the original embedded method, the projection-based version, and my method, so the local method. I performed some convergence analysis, and the error indicator is the L2 pressure error in the matrix, where the sum is taken over the intersection between coarse elements and reference matrix elements. And it should be noted also that we only consider in the reference grid only the matrix elements and not the fracture one. And here we give some data about the equidimensional solutions. So for the horizontal fracture case, I've used a rectilinear grid, and I have something like 1 million matrix elements and 10,000 fracture elements, and I've used a standard 2-point flux approximation scheme, so the standard scheme with 2 points. So I have a stencil with 2 values of the pressure, and an oblique, and the case of the oblique fracture, where I have a triangular matrix grid, and in the fracture grids instead I have quadrilaterals. So we have more or less 1,500,000 of matrix elements and 5,000 fracture elements, and in this case the virtual element method of order 2 has been used. So if we look at the convergence for the oblique fracture case when, let's say, the permeability ratio is high, we see that more or less the 3 methods have the same trend of convergence, so a linear convergence. The same if we lower the conductivity contrast. While if we now pass to the horizontal fracture convergence for a very high value of the contrast, we see that obviously the original embedded method does give high errors, while and so that it doesn't converge, while both the local and projection-based method do converge. If we now pass to the case of a lower conductivity contrast, we see that in the case of the projection method, the curve begins to flatten flatter while the grid is refined, while this doesn't happen for the local method. If we now pass instead to the oblique fracture case, the result is more extreme than before, in the sense that the projection method, as the grid is refined, gets worse and worse, almost reaching the values of errors of the embedded method. And this, luckily, doesn't happen for my method, so for the local method. But if we now, okay, and this is confirmed by the pressure maps. So here we have the local method where we see that the pressure jump is clearly caught, while in the projection-based case, it's almost a linear pressure in the y direction. So here we are instead looking at the convergence for the, let's say, value of the contrast, which is less than before. And in this case, both the local and projection method doesn't behave so good. But at least I would say the local method has, let's say, a monotone trend in the sense that the error keeps diminishing also, even if, let's say, when the grid is being refined, it reaches almost a constant value of the error. So, and these are the pressure maps. We see that this. Let's say that the conversion is not caught also by these pressure maps. So, what I want to do is to get better results for intermediate conductivity contrast for my method, for the local method, and hopefully, obviously, reaching convergence. So a solution is that replacing the matrix local problems with a technique, let's say, method is called Multiscale finite volume method, which requires the construction of a dual grid. So the one highlighted with solid lines. So the normal grid is the one with the dashed lines, while the solid one is this dual grid, and the cells of this dual grid are named interaction regions. So what I've done, one has to do is to solve 4 different types of local problems in each interaction region cut by fractures. And this, with this procedure, we get some transmissibility matrices, which are used to construct 9-point stencil modifications of those grid cells to which are associated these interaction regions. And since we have a 9-point stencil modification, obviously it's a multi-point-like method, and multi-point methods are known to effectively capture the full tensor permeability effects. And we can say that the fractures behave as an object that introduces full tensor effects, since it provides, let's say, the main path for the flow. So here it is some preliminary results with this modification of the local method, and we see that in the case of a high permeability contrast and in the case of an impermeable case with a high contrast, let's say, for coarse grids we have better results than the original local method, but as we refine the grid, then the original local method gets better. While if we look at the intermediate conductivity contrast case, it seems that the modification of the local method is always the best method for all refining grid ratio. In particular, for coarser grids, we have more or less the same results of the projection-based method, but let's say more in-depth studies are being carried out in order to, let's say, understand why this happens. And that's all. Thank you.
Do we have, since we're over time, do we have some short questions?
Thanks for the presentation. I was wondering how you construct your reference solution for the convergences. So I would guess, I'm not too sure about this, correct me if I'm wrong, that there are error estimates for for problems with fractures.
Mm-hmm.
Right? So where's the problem? Like, is it maybe that your preconditioners are less effective in those regimes?
I don't know. Actually, here I'm not. I'm just solving directly the equation, so without using iterative methods or preconditions or something like that.
Okay.
So
No clue why the error is actually staying up there with some methods?
no. That's the point. That's the point. Yeah.
Because you kind of get a mixed formulation at some point with respect to local.
Yeah. With the VEM, I'm considering them a mixed formulation actually. Same. The pressure that you see for the object fracture is picked from let's say a mixed. Let's say taking only the pressure of a mixed solution. Let's say.
Okay. Well, I can ask you.
Yeah.
We were over time.
Maybe you've already said it, and I
Yeah.
missed it. You said it's just incompressible case.
Yes.
So it's liquid fluid flow. Okay.
Yes.
So have you considered the possibility of having two different liquid phases, just like water and liquid phase, liquid like oil?
Yeah, that's the next step. Should be the next step. But let's say things are already complicated now, so we are. Let's say I'm focusing on understanding why have these convergence trends, and say that obviously is a thing that is was more concerned with the real things and with, for example, with the oil industry. So. Those kind of equations or multi-phase equations are those that actually are of more interest and not single phase. Yeah, I agree with it, but maybe in the future.
Then we thank again the speaker.